Chapter 24, problems only. So I'm looking at number. Now, no one look in the back of the book to make sure I'm right, because I just slow down the process.
I already wrote them all down, so I don't have to.
Oh, bummer. Determine the maximum high voltage required to saturate the resistor. All right, so we have something that goes all the way to 5 volts, but someplace I'm going to be saturated. I got 560 ohms sitting there, and I've got something over here that says 300. And I got 5 volts sitting there, and I've got a resistor sitting there, 3.3k ohms. Right. So what do you think? We've got some gain. Let's see. The current through the collector is going to be 300 times the current through to the base. That's what that's telling us, right? Basically. All right. So. And I've got a voltage drop here of 0.7 across that diode. And I've got some current flowing. When the current flows through here, when this guy gets real high, then I'm going to have current flowing through there. Okay, so I think I see that. I have some voltage at the base, minus 0.7. divided by 560 is going to be the current at the base. And then the current at the collector, current through the collector is going to be 300 times that voltage at the base minus 0.7 divided by 560. Okay, I'm in saturation when I have maximum current flow flowing here, right? So that would be the entire 5 volts, but I still have a 0.7 drop. So I'm going to go 5 minus 0.7 divided by 3.5K. That's going to be the maximum saturation current through that way is going to be 300 voltage at the base minus the 0.7 drop divided by 560 ohms. Okay, now I got one equation, one unknown, and I should be okay. 4.3 divided by 3.5K is equal to, now let's see, we'll put a 300 on the bottom, we'll put a 560 on the top, and we'll add 0.7, and that's going to be the voltage at the base when we are at saturation. Now, let's see if I can make my calculator work. 360 divided by 300 times 4.3 divided by 3500 plus 0.7 equals. And I show 700 millivolts. So at 700 millivolts on the base, this thing is going to be in saturation. And Chase isn't jumping up and down telling me I'm wrong, so that must be right. Although I told him he couldn't tell me I was wrong, so that is okay too. So number 19, determine the values of TD. TR, TS, TF. All right. So we'll start with the last guy. Time to fall. All right. So I've got 190 nanoseconds. I have 120 nanoseconds in the falling range there. So 190 minus 120, 70 nanoseconds. Okay, what is the delay time? Well, the time that I start going up until I see it starting to go up, 20 nanoseconds. 20 nanoseconds. Time to rise. Rise time is between 10% to 90%, so it'd be 80 minus 20, 60 nanoseconds. Time to saturation. Time to, what is that? TS. What is TS? Huh?
Storage time.
Oh, storage time. Storage time.
Time before it comes out of saturation.
So that's the time.
T3.
Yeah. Input transition occurs. So my storage time is 120 seconds. Nanoseconds. Because I go and I start coming down, but I don't start coming down until I start coming down. All right, well, that was 19. Moving on to 23. Is this color okay, or would you rather have a different one?
Yeah.
Too bad. Determine the trip point, the upper trip point, and the lower trip point for the guy in 47. So that's the guy underneath. Okay, so now we're going to have to go find a similar circuit. All right, I see it on page 861. I see a similar circuit. And using the Schmidt trigger up above. Okay, so the upper trip point on page 861, equation 24.7 minus Rn over Rf1 minus V out plus 0.7. And the lower trip point minus Rn divided by Rf2 plus V out minus 0.7. All right, so that's what we're looking for. Okay, so I got my finger on both pages, and I find the upper trip point to be minus Rn 1K. Oh, that's interesting. They got it marked R. 1K divided by Rf1, 5K, times minus V out. Okay, what is V out going to be? Okay, V out is going to be 9.3 volts plus 0.7. At any moment, I expect somebody to ask me how I got that, but I'll probably tell you to pack sand, because that type of guy, you know. Okay, so I got 1/5 times 10. No, that's not 10. That's, oh, never mind. Make this a 10. All right, that's better. 1/5 times 9.3. Upper trip point 1.86. Lower trip point minus 1K divided by 10K. 10 volts minus 0.7. So I've got 1/10 times 9.3 minus 0.93 volts. Now, this plus or minus 0.7 thing is associated with the diode itself, and so the voltage out that they use is the voltage in. And that's why I changed those to plus or minus 10. All right, good enough? 23, 27. Schmidt trigger 51. Okay, guide below. So I'm going to find the upper and lower trip point. Okay, there he is. I see him. He's on page 861. So I'm using my upper trip point is RF2 over RF1 plus RF2 times V out. And my lower trip point is RF2 over RF1 plus RF2 times minus V out. All right, well that should be pretty easily what we got. Back to the picture. Okay, so RF2 over RF1 plus RF2. We'll see that we're using the same thing twice. 11K divided, that doesn't look like 11, divided by 33K. So that looks like that's 1/3. So my upper trip point is going to be 1/3 of the voltage out, and my lower trip point is going to be 1/3 of the minus voltage out. And it looks like it's about 16. 3 doesn't go into 16. Bummer. Why can't 3 go into 16? 5 1/3 or 5 1/3. 5 1/3 minus 5 1/3. And 27, moving on to 35. Okay. 1001, moving on to number 35. Oh, some people. All right, is that better? All right. 35. $34, $35. Assume the value of RS shown in 56 increases to 10K. Recalculate the operating frequency, duty cycle, pulse width of the circuit. Okay, so RB is going to 10K. And the circuit we're looking at is on the previous page. So on the previous page, 56. Okay, so I've got a 555 timer. And now I got to figure out how is the 555 timer wired. And I've got a capacitor. I've got a resistor. It's not that one. 870. Oh, okay, I see it. On 870. Okay, so there it is on 870. It's a voltage control oscillator. And the reference voltage, blah, 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 blah. How in the world am I going to do that? Voltage control oscillator.
The equations for calculating are 870.
870? Okay.
Output frequency, pulse voltage, duty cycle.
All right. So I want the output frequency. 1.44 divided by RA. 10K. 10K plus 2 times RB, which is also 10K, times C1, which is 0.01 microfarad. Let's see. I better put parentheses here so that it looks like we're doing the problem right. All right, I'm ready. 1.44 divided by 30K divided by 0.01 micro. Do we get 4.8K? 4.8K. Pulse width. .693. What's .693? Anybody know? Is that 1 over pi? No, it can't be 1 over pi. Is it 2 divided by pi? 2 divided by pi. Syntax error. 2 divided by pi. Yeah, that's 2 divided by pi. All right, so, which is basically the thing we use when we find the average voltage of a sine wave. We use 2 divided by pi to get that. 0.696. All right, so 10 k plus 10 k times 0.101 microfarads. Okay, so I've got 0.693 times 20k times 0.01 double E minus 6. Looks like 140 microseconds is the pulse width. Yeah, that's what it looks like. And we want the duty cycle. Is that all we want? We want the pulse width, operating frequency, duty cycle. Oh, I wanted the duty cycle second. Duty cycle. 10k plus 10k divided by 10k plus 2 times 10k times 100. And we ought to better do that in our head, right? So this is 20 divided by 30, so that'd be 67% would be the duty cycle. No problem with that. That's 35. So what we'll do is we'll switch over to multisim, build this thing, and see if it really does that. Because if it doesn't, then what good are we? Yeah. But it doesn't matter what my, okay, so, what? I'm in Maple? Oh, we'll switch over to Maple and see if it works. No, I guess that'd be too hard. You could do that. You could put in the right differential equations in Maple to simulate the circuit. And there's a Maple sim that's out there that's only a mere $500 that you can buy, and it'll take your electronic circuit and give you the differential equations for it. So, all right. So what do we need? Where is the 555 counter anyway? It's probably
somewhere there.
It's probably not there. It's probably miscellaneous digital things. Is it there? No. Miscellaneous. Miscellaneous. Where's the 555 counter? Virtual miscellaneous. Blah, 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 miscellaneous, those things down that way. No. TTL? TTL. You trying to tell me you didn't really know?
Yeah, you've been following the line here.
Electromechanical, RF, advanced peripherals, miscellaneous, power components, indicators, mixed guys, 555 timer. Oh, yes, we found the 555 timer. Now, we seem to have a problem now. I can't see the stupid 555 timer. Okay, so Does it matter how many volts I put on it? Okay, so I got some voltage. I need a ground. Alright, so there's a ground. Thank you very much. I don't want another ground. Alright, so I'm going to put voltage up to VCC, and I'm going to hook ground to ground. Okay, and then we're going to go and put an oscilloscope. Put an oscilloscope over here so we can see what the way to go. All right, then we need two capacitors, two resistors. Resistor, where's my resistor? Two resistors, 1, 2, and one capacitor. All right. And we want one to be 10K. And the other guy to be 10K. And we want this guy to be 0.01. Alright, looks good. Back to the original circuit, and let's see, we're going to go from one of these guys to there, to the power supply, from him to there, from him to the capacitor, and then from the capacitor to ground. Okay, that looks good. Pin 8 is already connected. Pin 4 is going to VCC. Okay, pin 7 goes to between the two resistors. Pin 6 goes to between the resistor and the capacitor. Pin 2 goes to where pin 6 went. And pin 5 is not connected. Okay, did I do that right? Voltage out. Pin 4. Alright, pin 4 is the reset guy. He's supposed to go to VCC. Ah, well, we'll see if it works. Where's my other ground? There's my other ground. Bring it over here. Turn this guy on. Turn that guy on. And what do we see? Diddly squat. Absolutely nothing when you know it. Alright, so what should we do first? Get rid of the stupid oscilloscope, right? And put a simpler one in. Where's the simpler one? Right there? Yeah, that's better. So we'll hook him up to there. He's going to be hooked up to ground. And I still don't have a signal. Okay. Pin 5 not connected is fine, but pin 4. VCC, does that mean 5 volts? Does VCC means 5 volts? Yeah. Alright. we'll put, where's power supply, VCC. Thank you very much. I don't want 2. And we'll hook him up there. Boom. Oh, there we go. All right. Now we're fine. Anybody remember what our answer was? Okay. Does that look like I'm up 2/3, down 1/3? 1, 2, 3, 1. Yeah, it does. Yeah, it looks sort of like this is 2/3 and that's 1/3. That's we'll move this guy. Thank you very much, and we'll move him over. Darn. Be that way. Just not letting me move him at all. Okay, well that's about right, isn't it? So what's 233 microseconds? 1 divided by 233 double E minus 6 equals 4,300. So what did we say it is? 4,800. So if I could put these guys in the right spot, which I'm not sure why I can't. There we go. That's better. We'll use my finger. Much better. Okay, that's about right. And then we say if I go 330 or 333, I remember that guy, and I come over here and I call that 150. So if I go 158 divided by 233, I get 67%. So my duty cycle's right. My frequency is about right. What was the other thing my pulse width? What was my pulse width supposed to be? 140, and so if I go in and go to there and go to here, that's close enough. Okay, so all right, so if I tweak on this one, so it looks like we're okay, and that's good enough. All right, back to doing the last problem so we can go home. Anybody for that? 43. Now I lost my place in the book. 43. Refer to problem figure 59. Okay, I'm referring to it. Okay, see it right there. I'm referring to that figure. Okay. The LED should light when the positive going impulse pulse passes the upper trip point of 1.7 volts. The LED should turn off when I reach the lower trip point, blah, blah, blah. These are the requirements. Okay. Unfortunately, there are 2 flaws in the design. Find the flaws and correct them. Okay, 2 flaws in the design. Okay, first of all, is the upper trip point 1.7 volts? That's going to be the first question. So we'll look at upper trip point for this guy. Is okay, so the upper trip point is RF2, 2.9K. 2.9K, I'm looking on page 862, divided by 3.9 plus 2.9K times 5 volts. So that should be the upper trip point. 2, that's not a 2. 2.9 divided by 6.8. 6.8 times 5. So the first flaw is my upper trip point is at 21.2.13. And it says that it's supposed to turn on when the upper trip point is 1.7. So that's a first flaw. Lower trip point is going to be the same. It's going to be minus 2.13 when it's not that either. So both the upper and the lower trip points are wrong. Are those the only two flaws? There are two flaws. Find the flaws and suggestive action. Okay, so the next flaw, well, we're going to assume that that's one flaw. How much current does it take to turn on a light emitting diode? And the answer is 15 milliamps, right? So it's 15 milliamps. How does that compare to 5 minus 0.7 divided by 2.2K? Because the maximum current through RC is going to be that. And it's going to be bigger than 0.7, but that's going to be our first thing. So 4.3 divided by 2.2 EE3. I only have 1.9 milliamps. And at 1.9 milliamps, the LED will not turn on. So the first flaw is I got the trip point wrong. The second flaw is that I have a current limiting resistor that won't allow the diode to turn on. All right, so I found the two flaws. We'll then go back to multisim and see if we can build a circuit. And so I need one of these guys. I need one with yeah, I need that one. Okay, so I'll take that guy, and then I need 4 resistors. One, 2, 3, 4. I need 4 resistors. I need a light emitting diode. What color light emitting diode do we want? Orange? Okay, so we use a light emitting diode. I need a transistor. Any particular transistor? That looks good. And I need a couple grounds. One, 2 grounds, and I need 5 volts. I should probably not use that guy. I should probably use a different 5 volts. Oh, bummer. Then I need a negative 5 volts. All right, well, here's the negative 5 volts. Okay. So now I got a positive 5 volts and a negative 5 volts. I'm going to cheat and call that minus 5. All right. And I'm going to put these two guys over here. Do a rotate on them. We'll rotate that guy. All right. Hmm.
Quiet, people, please.
Sorry, sir.
12.
Okay, we turn it on, what happens? Oh, it's going to work because I don't have the right stuff in it. Okay, that's fine. So if I change this to 2.2K, and I change that to 100K, and 3.9K, $2.9K, and I turn it on, and lo and behold, it doesn't work. All right, so now we're going to go back and look and see. We'll look for the upper and lower trip point of this guy. Oh, turn on. That's good. Okay, so I see my lower trip point at minus 2.1 volts, and I see my upper trip point at plus 2 point what volts? Plus 2.1 volts, which means the upper and lower trip point was wrong, which is what we said it was wrong, right? And then I look at the current. We'll go and get rid of this guy. And we'll throw an ammeter in there. Now, did it hook up or did it not hook up? Yeah, it hooked up. Okay. And we throw an ammeter in there. And we see I don't have enough amps flowing in the circuit to turn on the LED. So that's my other fault. Now, are we supposed to correct these faults, or are we supposed to just tell you what? Find the flaws and suggest corrections. Okay, so now we're going to suggest a correction. All right, so first of all, we're going to figure out what this guy should be. So if I go 5 minus 0.7 divided by some resistance, I want that to be at least 15 milliamps. And so R is going to be 4.3 divided by 15 milliamps. 4.3. Going to be more like 280. Okay, so we'll come back and put in a 280. Is 280 a standard value for a resistor?
No.
Okay, so I'd have to use a standard value. That'd be 270, right? 270, I think, is a standard value. And now we have 3 milliamps, but that still isn't enough. So we go back and say, well, yeah, I accounted for the 0.7 drop across the transistor, but there's a 1.4 drop across the light emitting diode, so we'll go back and recalculate. This should be 5 minus the 0.7 minus 1.7 divided by 15 milliamps.
Isn't there a drop on the diode too?
That's what I'm getting, yeah. 5 minus 0.7 minus 1.4 equals divided by 0.015. So this looks like a 190. Is 190 ohm, is that a standard resistor? I don't think so. I think it's 180 is the standard guy. So we'll go to 180. Boy, we're still not getting enough. Still not getting enough current to turn it on. So that being the case, theory of practice says cut it down more. 90. We're never... What? Yeah, but the other problem is working just fine. It's just turning on at the wrong spot. That's not an issue. The issue is the light emitting diode's not coming on. And
Well, would it be the 2014 though on the compensation for the drop though?
but we're changing this guy.
But it's that, oh, I see.
See, we're limited by the amount of current we have, and it looks like we're not limited by the current limiting resistor, but by the voltage. It looks to me like that's what we're limited by.
Change that to 6 volts.
So it looks like we're going to have to increase our voltage. There we go. So if we increase our voltage, we'll be okay. Now we got to get the trip point right. We can probably come back to this guy and change him a little bit. We'll change him back to 190 and see if that helps any. See if that changes anything. All right. So we like 190. The guy's flashing. Now we got to get our trip point right, and the trip point is supposed to be 1.7. All right. So we come back to our trip point calculations. And we want this to be 1.7. So 2.9 divided by 2.9 plus something times 5 volts. We'll go with 5 volts. 5 is supposed to be 1.7. 2.9 times 5 is equal to 1.7 times 2.9 plus 1.7 R. R is equal to 2.9 minus 1.7 times 5, 2.9 divided by 1.7. And that's going to be in a K. 5 times 2.9 minus 1.7 times 2.9 equals divided by 1.7. I should have a 5.6 K in the other spot. All right, so I come back here, and this guy's supposed to be 5.6 K. 5600. Turn it on. I still flash. Where do I come on? Okay, so there's my upper trip point. There's my lower trip point, and if we could see what it was, 1.9 and 1.9. So we have 1.9, 1.9, and we want 1.7. All right, so we got to tweak on it a little bit more. Not much though. We'll tweak on it up to 6.6, 66. 6600. there, and there. Bummer.
Much.
Too much.
They have to be lower than 50.
All right. So we'll go halfway. Where were we before? 5, 6. So we'll go with 62. Oh, way to go. All right, turn it on. Yeah, it looks like the lower trip point. And there's the upper trip point. And now we're looking better. How come we have minus 1.6, but I don't have minus, that should be the same amount. Oh well, we'll say that that's all right. Close enough. Hmm? Not going to disagree with that? All right, gentlemen.